So sorry, I could not take the lecture yesterday. I was not well. So I will take one additional lecture, but not now, after the minor, because before minor I'm taking 2 courses, so I will not have time. But after minor, one day I will take one extra lecture to make up for the lecture that I missed yesterday. Okay. Anyways, so in the last lecture we started talking about limit state function, and in limit state function we defined limit state function. If you remember, we defined limit state function G as C minus D, right, where C was the capacity, the maximum capacity of a system, of a building, of a structure or whatever. D was the demand, which was demand means it was coming because of the load, let's say maximum deformation, maximum stress under action of some certain loads and all of those things. From here, I said that if I have, let's say, this is my D, this is my C PDF, this is my FCC, this is my FDD, then the probability of failure I said was given by the area under the curve, right? Now remember, last time also I said it, but I did not make it very explicit. So when I am saying it is given by the area under the curve, I am talking about it from an intuition, from an intuitive basis, or rather from a qualitative basis. I am not saying that if you quantify that area, that will be exactly equal to a probability of failure. No, that is not what I am saying. I am saying intuitively that is the area that is contributing to your probability of failure in one way or the other. So it's more about a qualitative representation and not a quantitative representation. Quantitative we anyways did last time, and I will write that down again now. So this is qualitative representation. And why do I call it qualitative representation? It will become very clear. Let's say C and D are well apart. In that case, forget about this graph. What is the probability of failure? 0. What will be the area under the curve? 0. If C and D are very close, the probability of failure will be higher, and if they come close, the area increases. Also, what happens if the dispersion or the variance increases? If the variance increases, the area will increase, which means the probability of failure will increase, and we know that if the variance increases, uncertainty increases, so probability will in this case increase, right? So here, when I say that this represents the probability of failure, that is from a qualitative sense, that is from an intuitively, right? It is not based on like you will actually calculate the area and that will match, not from that sense, okay? So this is qualitative representation of probability of failure. I am now going to start writing it as PF, okay? PF will stands for probability of failure, okay? And this means that, so that if CFCC moves in the right direction, towards right, maybe moves towards right, PF reduces, and that is quite clear because then C is always going to be greater than D. And along with that, we also see that the area reduces, area under the curve. When I say area, I mean this area. Let's call it A. So when I'm saying area, I mean this area A. And similarly, when they come close, the area increases, and we also know the probability of failure increases. If standard deviation increases, we know probability of failure will increase, and that is again something that we observed, right? So in that sense, now, and this is all, I will highlight this, qualitative, okay? So these are all qualitative. This is the important one, okay? Now quantitatively, we already did it last time. Let us quickly recap it. So if you have to quantify it, then we saw that reliability was equal to integration minus infinite to infinite f d d integration d to infinite f c c dc dd, right? This is what we saw last time. And how did we arrive at that? We took a small d, and for that given d, we will say that the system is safe, it is reliable if c is greater than that d. And then if we integrate for all the values of d from minus infinite to plus infinite, we arrived at that. And this is something we did last time. And similarly, probability of failure was equal to, this was equal to integration minus infinite to infinite f dd. So this is basically selecting a d, small area, and then this will go from minus infinite to d now, because it is now failing, f c c dc dd, and then obviously this is nothing but my CDF. So, and that was giving me the final expression, which was integration minus infinite to infinite f d d capital F C d dd. Okay. And this is how you can quantify and calculate the probability of failure. Okay. Given that, obviously there is an assumption that you know C and D, you know the PDF of C and D, and there is one more assumption here. Can you tell me what is that? In this expression, there is an assumption I have taken. I have assumed that C and D are independent. If I don't assume C and D are independent, I cannot take that FCC. It will become FCC given D. So here there is an inherent assumption that I am taking, that C and D are independent. Capacity and demand are independent. Capacity will not change with demand. And because of that, I have separated the two PDFs that you are seeing. Otherwise, it will be probability of D will remain as it is. The other one will be PD C given D from the product law, and that we have seen earlier. Okay. So here there is that assumption is there, right? So note that we assumed C and D to be independent and D to be independent. Now remember that last time also I said that this is all good on pen and paper. If I give you the PDF of C and D, you can use it and find it out. But in reality, you are not going to know the PDF of D. PDF of C you might still know. PDF of D you are not going to know. And so this will be not that useful. And today we will see that if this is not useful, what is useful, and how we can actually use it in practice for real systems. But before we go there, let us take two case studies on this and see how this thing can be used for very simple case studies. Okay. So case study 1. Case study 1. And in this case, we are going to assume that C and D are independent. They already were, but they are also Gaussian. So in case study 1, we are going to assume that both capacity and demand are Gaussian random variables with a given mean and covariance. Okay. So here we assume that C basically is a Gaussian. So C and D are Gaussians, and we are going to work with this very special case. Okay, this is not a practical case, but this is a special case, and we'll talk about it. We'll deal with it. So in this case also, our limit set function remains C minus D. Okay. So now, assuming you have read the typed notes from the lecture 1, 2 and 3, can you tell me if C and D are Gaussian, what is the distribution of G? Gaussian. Why? Because if two variables are Gaussian, some of them are also Gaussian. So that is a property of Gaussian random variable. It only holds for Gaussian random variable. It is the additive property that if A and B are following Gaussian distribution, then C, which is equal to A plus B, will also follow Gaussian distribution. So there is a property like that, and you can prove it. It's very simple. You take the exponential form and then open it, and then you can prove it. Okay, I'm not going to prove it, but yeah. So we know that if C and D are Gaussians, then G will also be Gaussian. Okay, we know that, and it can be proved in a trivial proof, 2-3 sentences, 2-3 lines, and you can do it. So therefore, G is Gaussian, but that is not enough. I mean, saying Gaussian can be anything under the sky. We need to know the parameters of the Gaussian. What is the mean and what is the variance? So what will be the mean? Assuming you know the mean of C and mean of D. Property of expectation. Addition, if there was addition, in this case there is subtraction. So it will be subtraction. The property is expectation of A plus B is equal to expectation of A plus expectation of B. And this property is for expectation. It has nothing to do with A and B being Gaussian. These are more generic expression. Okay. So considering Gaussian of C given, let's call it mu C and sigma C square. So this means C is a Gaussian distribution with mu C and sigma C square. This is what it means. And the other one is also Gaussian, D mu D comma sigma D square. So considering these two, we can write consider these two, and using the identity. And what is the identity? Expectation of A plus B is equal to expectation of A plus expectation of B, right? And this is a known property. I am sure all of you are aware of this. So using this property and using the data from the Gaussian distribution, we know that expectation of G, which is mu of G, is equal to, we obtain mu of G is equal to mu of C minus mu of D. Okay, that is what we obtain. Similarly, can you tell me what will be the variance of G? What will be the variance of G? Yes, you can use that, but there is an identity for variance as well. What is that? Variance of A plus B is equal to variance of A, you're right, variance of A plus variance of B plus 2 times covariance of A comma B. So variance of A plus B is equal to variance of A plus variance of B plus 2 times covariance of A comma B. Now A and B, in this case C and D are, so what happens to covariance? So we will get covariance of C plus covariance of D. And in this case, because of the negative sign, the covariance was supposed to be negative. This was not. By the way, this important point came into my mind because of this. Remember that if x and y, two variables, are independent, the covariance is going to be 0. But it does not mean that if the covariance is 0, they are independent. Covariance only tells you linear dependencies. Okay, whereas independence is more global. Okay, so they are uncorrelated, linearly uncorrelated, but they may still be dependent. And one very easy example is take y is equal to x square and let x vary from -2, -1, 0, 1, 2. Calculate the covariance, you will realize that you will get the covariance 0. But obviously x and y are dependent because y is equal to x square. Okay, and it is coming out because y equal to x square is second order, it's not linear. Okay, but anyways, that was some other point I was talking about. Let me come back here. Similarly, sigma G square is equal to sigma C square plus sigma D square. Here I have used C and D are independent. Right? So therefore, finally, the distribution of G is equal to, so therefore, the limit state function is Gaussian G with mu G and covariance sigma G square. Okay, so that is my PDF of the limit state function. It has nothing to do now with C and D because the effect of C and D has been accounted for into this mu G and sigma G, and obviously the Gaussian. I mean, all of that has been accounted for. Now, if I want to find out probability of failure, how will I do that? What is the probability of failure? G less than equal to 0 or less than 0, right? And how do I find it out? So, probability of failure, integration of minus infinite to 0, f g g d, right? From the fundamental first principle definition, right? Now, FGG is Gaussian. So then what is this? This is the CDF of that Gaussian, right? How do you find the CDF of a Gaussian? Again, I'm assuming you have read the additional slides. But how do you find the CDF of a Gaussian? Or how do you represent it? By converting it into standard Gaussian and then using the standard Gaussian table or chart. And this was developed when there was no calculator, obviously, because this is much older, Gauss, right? Long back. So this basically you write as CDF of standard Gaussian. This is the CDF of standard Gaussian. And then you need to convert this G into standard Gaussian. How do you convert it? X minus mu by sigma. That's what we do. Now, in case of CDF, that X is my 0, because this is CDF at 0, minus infinity to 0. So this will be 0 minus mu g by sigma g, which is equal to phi minus mu g by sigma g. Okay. Any doubt? I'll repeat what I've done. So if X is a standard normal distribution with mu and sigma, you can convert to standard Gaussian. You can convert it to standard Gaussian, and this is known as normalization by doing the following operation. If you do that, you will get a z variable, and this z variable will follow a Gaussian distribution with mean 0 and standard deviation or covariance 1. And for this standard normal distribution, the CDF is represented by this form. This is the CDF of standard normal. CDF of standard normal. Okay. So the idea is that, or the idea was at least, now you are not going to use that, but you should know. So previously, as I repeated, right, as I said earlier, right, there was no calculator. Gauss was developed this much, and at that time what they did was they came up with a standard Gaussian table. They numerically integrated and came up with a table which stated the different values of phi for different values of z in the range, let's say, minus 6 to plus 6. Why minus 6 to plus 6? Because minus 3 to plus 3, that probability is 99.81%. Minus 6 to plus 6, 99.9% maybe. I don't know the exact number, but very high probability that it will be in that range. So that table was listed. So now whenever you have a Gaussian, you just convert it into phi, standard Gaussian, and then take that table, see the value and put it there. So that was the original idea, and that's why everything is represented in standard Gaussian. In today's time, that is not needed. You will just put it into a computer, it will give you. Okay. But even in computer, many of the times, even if you are giving the numbers only, it actually does by doing this. So you are giving mean and standard deviation. Inside the computer, some routine is there, mostly in Fortran or C++, which you are not aware of most probably because you are using Python or MATLAB. But they use these routines, and this is how they can compute. Okay. So this is giving you your probability of failure. Okay. For the Gaussian case, all you need to do is calculate the mean, and so from here we can generalize. You can imagine. See, C and D being Gaussian is not our criteria. For using this, what is our criteria? G's would be Gaussian. Even if C and D are not Gaussian, G is Gaussian, I can use this. And we are going to exploit that fact in a short while after I discuss two additional topics. Okay. Okay. Now here there is an important term that I can see, which is mu g by sigma g. That ratio is very important, and that ratio has a name. It is known as the reliability index, or to be more specific, Cornell's reliability index. There are other forms of reliability index. This is known as the Cornell's reliability index based on whoever developed it. Okay. So this one, right? I'm not going to consider the negative sign. Keep that in mind. This is known as, we denote it as beta, and beta stands for reliability index. So this is phi of minus beta. Okay. And my beta is my reliability, Cornell's reliability index. Now, any idea why is it called reliability index and not failure index? Because I am calculating probability of failure. but I am calling it reliability index or not failure index. Why? Because of the negative sign. Correctly. If the negative sign was not there, I will have called it failure index. But because of the negative sign, I know that the higher the beta, the lower the probability of failure, the safer my system. So beta actually, increase in beta indicates increase in this reliability or reduction in this probability of failure. And this beta is very important in a practical scenario. So often you will hear that this building is designed for a reliability index of 3. So they will not say probability of failure, they will say beta. But again, this beta has its own limitations. Like example, in this case, this beta, I have arrived it based on the Gaussian assumption, which might not hold, but among practitioners, this is a very common terminology. The reliability index, probability of failure is not that common. Okay. But in the scientific community, probability of failure is more common. Reliability index is also common, but PF or probability of failure is much more common. Okay, so keep that in mind. Okay.
But the reliability has nothing to do with the Gaussian, right?
With the
Gaussian system.
In reality, exactly, it has nothing to do.
Because it depends only on mu and validation.
No, it has, because that capital phi is Gaussian, right? And capital phi is becoming Gaussian because your G is Gaussian. So the limit state is Gaussian. So it has nothing to do with the C and D being Gaussian, but it has everything to do with G being Gaussian. Okay. Okay, let us take one more case. And in this case, we will consider, that G, not G, D and C, they are log normally distributed. Okay. C and D are log normally distributed. Now, can someone tell me what is log normal distribution? Again, additional slides you are supposed to read. What is a log normal distribution? You need to study it, but even if you don't know, the name itself is sufficient to tell. Exponential of a Gaussian distribution is a log normal distribution. Okay. So if you take suppose A is a Gaussian distribution, then exponential of A will be a log normally distributed variable. Log normally distributed variable, I am not going to details of the parameters and all of those things. This is the log normal distribution is exponential of Gaussian is all you will need for the discussion that will follow now. But you should read log normal distribution. It will not take more than 2 minutes if you search it on Wikipedia. You just need to search it on Wikipedia. You will get two parameters M and V, how they are related to mu and sigma, and how it looks. Okay. But because we are talking about log normal distribution, let me also tell you one more fact. Log normal distribution is exponential of Gaussian. So it is a non-negative distribution. So, and that is why it is very popular in modeling variables that are not bounded, but you know at least that they are not non-negative. So for example, if I am modeling mass as a random variable, I will not take it to be Gaussian, because Gaussian there is a probability, finite probability it will go to negative. Log normal is a better model because that will never go to negative. Okay. So mass is one example, and you can imagine many other height and all those things. So, and those are the places where log normal is generally used, non-negativity. Okay. Okay. Case 2, C and D are log normal distribution, and because I have not discussed log normal distribution, let's write it down that C is exponential of C tilde, where C tilde is my or is some Gaussian distribution, is some Gaussian. Okay. Similarly, D is equal to exponential of D tilde, where this is my Gaussian, right? This is from the definition of log normal distribution. Okay. Now in this case, and this is very important, we cannot take the limit state function as C minus D. I mean, we can, but then we cannot do things analytically. So in this case, what do you think the limit state function will look like? Because of the exponential is sitting there, C by D minus 1. Okay, C by D minus 1. Okay. So in this case, so this was the additional part, right? The limit state function G is equal to C by D minus 1, or rather C by D can be the limit state function, but then 1 is the threshold. Minus 1 means 0 is the threshold. Okay. I will work with 1 as a threshold, you will realize very soon. Okay, otherwise it will. And by the way, this form is needed because you have to remember that ultimately I will require the PDF of G. I will need that. Without that, I cannot proceed analytically. I can always proceed numerically, no one is stopping me. But here we are talking about things in an analytical fashion. And that is why this form is taken. Okay, clear? Why have I changed the form of the limit state function? But this is also important in this sense that this also tells you that you are not bounded by a choice of limit state function. If you know the limit state function, you can always choose how to represent it. You have that freedom. Like C minus D and C by D minus 1 are two equivalent but different forms, right? Okay. So now let us take C by D from here, and we know this is equal to exponential of C tilde by exponential of D tilde, and this is equal to exponential of C tilde minus D tilde, and this is the exact reason why that form was selected. And now C tilde is Gaussian, D tilde is Gaussian, C tilde minus D tilde is Gaussian. So exponential of a Gaussian is log normal. So then this will become a log normally distributed variable. Okay. So this is equal to exponential of G tilde. Okay. Which means this whole thing is log normally distributed. Okay, this whole thing is log normally distributed. Okay, so now what will be the probability of failure? I'll integrate this log normally distributed random variable from minus infinity to 1. Okay, not 0. So my probability of failure is now integration minus infinite to 1 PDF of G hat. Can you tell me why did I use G hat? Actually it is, maybe I don't need to. I mean, it is G actually. I was using G hat because the minus 1 I did not include when I calculated this. So that's why I was using, but I'm writing it in terms of G directly. So no, actually it is correct. It should be G hat because G is having minus 1, right? So it is correct. G hat, where your G hat is equal to exponential of G tilde, first of all, which is equal to G plus 1, right? So even for log normal, you can do it analytically. But the important point that you must have realized by now is that in most cases these things will not work. This is just to develop understanding, but in most cases this business is not going to work, right? So now let us go back and let us go back to G and let us try to see how we can use it. Okay. So now we are going to start a new topic, which is first order second moment method. Okay, and this is not a new topic as such. I mean, whatever we discuss now is going to motivate this, and you will realize that it is actually nothing new. But anyways, there is a name and you should know the name. So generally the first four is what we use it. So we call it FOSM. First F, order O, second S, moment M. So we call it FOSM. Okay, and that is a common term. Okay, so now for the Gaussian case, and Gaussian case I mean case 1, right? So for the Gaussian case, what did we observe? We observed that if limit state function is Gaussian, the probability of failure is phi of minus beta or phi of minus mu g by sigma g. We observed probability of failure is equal to phi minus mu g by sigma g. Okay, and this first case means, okay, let it be here. Okay, in the first case we observed that. So if we generalize it, we can always say that as long as the limit state function is Gaussian, this will hold. Okay, so generalizing as long as g is, and g is my limit state function, is Gaussian, Pf is equal to capital phi minus mu g by sigma g. And this is what is kind of obvious, right? Now, before I go ahead, let us try to see why the name. First order we will talk about later, but it is also called second moment. Why is it called second moment? Look at this expression. What is the first moment of a random variable? Mean. Second is expectation of x square or variance also, as I said. So now in this, for finding out this probability of failure, you only need information up to the second moment, mean and standard deviation, and that is why it is known as second moment method. Correct? Why do we only need information up to second moment? Because our limit state function is Gaussian, and for defining Gaussian, only information up to second moment is needed. The Gaussian distribution, the parameters are mean and standard deviation. So because of that assumption, this is happening. Okay. So this is called second moment because, or rather we can see that only first two moments are needed, right? And that's why we call it second moment. Okay, not third moment, not fifth moment, not nth moment, second moment. Okay. Now to understand why we call it first order, actually it is not first order as of yet. Whatever I was discussing was based on the case 1. So now the first order will come into picture, but before that comes into picture, we ask a simple question. The question is that in most cases, my limit state function will be non-Gaussian, or rather, let me put it in a better way, in most cases, I will not be able to represent my limit state function using capacity and demand. It will be represented using generic random variable x, and it will be some nonlinear function of this capital X. If you think about even the simplest example that we took last time, which was L by 325 minus PL cube by 3EI. L was having a cube. So even if L is a Gaussian random variable, all of these are Gaussian, clearly demand is not a Gaussian random variable. And we don't even know when there is cubic of Gaussian what random variable that is. So even for that simple problem, it was not Gaussian, right? So we cannot ensure that C and D will be Gaussian, and more importantly, we cannot represent, maybe in many cases, we will not represent this limit state function using C and D. We will directly use a generic expression, which will be not in terms of C and D, but in terms of X, right? So, but this only works when G is Gaussian. This only works when G is Gaussian. For a generic real world problem, my limit state function will be of the form G of X, where X is my generic random variable. So for a real world problem, the limit state function is G of X. Okay. Now previously I was using capital G, I made it small g because capital G was denoting as random variable, whereas G is like a function. So for a given X, you will get a sample of the random variable. So I use that. Okay. It will be of the form of G of X, where X will be some or in X is a random variable with some distribution. So it's a random variable with some distribution. Okay. And not only that, even if this X is a Gaussian distribution, even if this X is Gaussian, having Gaussian distribution, even in that case, this G will potentially be a nonlinear function like PL cube by 3A. This G will have some nonlinearity in X. This will be a nonlinear function. Okay. This is clear. So now, clearly with this setup, phi of minus beta is not applicable. That will only be applicable if my G is coming from a Gaussian distribution, right? So this phi of this thing will not be applicable, right? So the question we ask is, can we somehow use I have not given any equation number. Let's give it equation number 1. Equation 1 for generic nonlinear, generic means nonlinear, linear, everything. So generic G of X. Okay. And generic G of X means that X will have some random distribution which might or might not be Gaussian, and this G will be some function which might or might not be linear, right? So can we use it? Can we somehow use it? So can you give me some idea how we can potentially try to use it? What can we do here? Transformation of what? That is one, that will solve one of the problem. So one of the problem is X is non-Gaussian. We want to make X as Gaussian first of all. And how to make X from non-Gaussian to Gaussian? Transformation. That is one step. But even if we transform it and make X into X tilde, which is Gaussian, still this G is non-linear, right? So still we will not be able to use it. So we will need more things. That is the correct step, by the way. That is correct, but that is not enough. What else? I have transformed X into Gaussian, so let's assume X is now Gaussian, okay? But still I cannot use it because G is non-linear. So what can I do? Linearize. How? Yeah, say Taylor series. That's what I always do. Solid mechanics, fluid mechanics, everywhere. So if we can somehow linearize it using Taylor series expansion, then it will become a linear function of X. And I've already made X as Gaussian following his recommendation. So in that case, it will be a summation of Gaussian or something like that, which will make G as Gaussian. And if G is Gaussian, then I will be able to use phi inverse of minus beta. Clear? And obviously, when I say with Taylor series, I will linearize, you can imagine where you will truncate? After first order or at the second order, whatever you call it, right? So I'm retaining up to which order? What was the name of the method? That's why the name. So the name is because I have to use Taylor series, retain up to first order. So the name first order comes into picture. Things become Gaussian. So now I will use the first two moments, second moment comes into picture, and I will compute my probability of failure. So let me write it down and then we'll stop. Next class we'll start with two examples and talk about the limitation of this thing. Okay. G, we have not taken G to be nonlinear. We are saying G is generic, which means G can be linear and can be nonlinear. And in most cases it will be nonlinear, like the cantilever example case. Okay. If G is linear, then that's the best case scenario. You don't have any approximation. So yeah, to do that, we need two things. What is it? So do that, I need two things. First is transform X to Gaussian. How to transform X to Gaussian we have not yet discussed, and we are not going to discuss now, but I will discuss it. I'll devote one lecture to discuss this. There are in particular two methods which we will use. One is Rosenblatt transformation, the other one is Nahtaf transformation. So there are two ways, Nahtaf, which is the better one, and then Rosenblatt, and then inverse CDF and all those things obviously. Okay. And then the second thing is linearize Gx using Taylor series. Okay. And if you do that, you will end up with a linear expression. Okay. So that is basically what you are going to do. Taylor series expansion, let us look into it. Can you remind me what is the Taylor series expansion? G of x is equal to, first I am talking about when x is scalar. Forget about x being vector. What scalar you tell me? G of x naught plus G dash, which is dg dx evaluated as x naught and then multiplied by x minus x naught, which is like the h, right? The difference. This is the first order Taylor series. So not the first, obviously first order, but also single variable. What if x is a vector? Then So this will be g of x naught, but x naught is a vector, so it is like x1, x2, x3, x4, something like that, plus summation I equal to 1 to, assume n variables. This will become partial del xi evaluated as at, this is at all of the vectors, xi minus x naught I. So I will call it x0 I, right? And I'm only writing up to the first order. Second order you can imagine. Okay. Second order you can imagine. I'm not writing it right now, but I will have to write, by the way. Okay. And we'll do it next time, where you will realize that if I write only up to the second order, variance will create problem. Mean you can evaluate, but variance will create problem. So I don't have time today. So we'll start with these two expressions next time and proceed from there. Take examples. So that will basically, by the way, what I'm talking about now is now MV FOSM. What is MV stands for? Because I've already taken x to be more than one variable. Okay, both are same basically. First order, I mean single variable Taylor says, multivariable Taylor says, nothing changes. But I'm already talking about MV FOSM. Next class we will complete MV FOSM and try to go into something that is more useful and more practical. By the way, for homework 1, you can expect some programming from MV FOSM and from FORM also, which I'll cover next. Okay. That I have sent an email today, topics. So check it out. I will circulate, create some form or something where you can give your choice tomorrow. Okay. So I'll stop here. Thank you.